Hello everybody, today we're going to talk about factorial designs, which is when you have two or more independent variables. So, when you increase the number of independent variables, we call that a factorial design. And you can have two or more. In this case, we're going to talk about two independent variables. And the independent variables then become called factors. Each independent variable becomes a factor, and therefore we have a factorial design. And when we talk about factors, we're trying to explain or explanatory factors which are your independent variables that would explain the variability in your dependent variable. So when you're thinking of something, and let's just use one example here, depression as our dependent variable. Up until now, we've only had one independent variable. We've looked at, let's say, I don't know, marital status. If you're married or single, does that affect levels of depression, or gender, male versus female and levels of depression, or student status. Are you a student or not a student? And does that affect level of depression? But in the real world, it's much more complicated than that. There's probably not just one factor, right, that explains why people have higher or lower levels of depression. There's probably many factors, such as, right, could be marital status and gender and student status and I don't know, family satisfaction and socioeconomic status and all sorts of things that would truly go into somebody's level of depression as the dependent variable. So up until now, when we've had one independent variable and one dependent variable, that's a very simple study. And in reality, we often make our studies more complicated to try to make things a little bit more real world. So we might have multiple factors that we put in a research study to try to explain, in this case, the dependent variable of level of depression. So the simplest of the factorial designs is what we would call a 2 by 2 factorial design. And 2 by 2 means we have two independent variables, two factors, and each one has two levels. And there's one dependent variable, so that doesn't change. The dependent variable is always just one. So for example, here's a 2 by 2 study. We're looking at age as one factor, and we're going to test 6-year-olds and 10-year-olds. And test interval, so this is a memory test, and we're either going to look at immediate, so you give someone a memory test, let's say a list of words, and then ask them immediately to tell you the words, or delayed test interval, meaning you tell someone a list of words, and then in 20 minutes you ask them to remember the list of words. So we have two factors, right? Age and test interval. They each have two levels, age of 6 and 10, immediate or delayed. And the dependent variable is memory performance. So in terms of factorial notation, when you have a 2 by 2, the first number, whatever it is, in this case it's a 2, but the first number represents the number of levels of the first independent variable. The second number, whatever it is, represents the number of levels of the second independent variable. So each number that you have there represents a variable, and the magnitude, or what number it is, represents the number of levels of each independent variable. And then you multiply these two numbers together to get the total number of conditions or groups. So in this case, how many conditions do we have? We have 2 times 2. We have 4 different groups. And that makes sense. We have 4 groups. We've got 6-year-olds who are taking the immediate memory test, 6-year-olds taking the delayed recall test, 10-year-olds taking the immediate recall, and 10-year-olds taking the delayed recall test. So in this case, if we have a 2 by 3 by 4 by 2, how many independent variables do we have? Well, we're just counting the numbers that are there. So there's one number 2 numbers, 3 numbers, 4 numbers. We have 4 independent variables. How many levels of each independent variable? The first independent variable has 2 levels. The second independent variable has 3 levels. The third independent variable has 4 levels. And the fourth independent variable has 2 levels. And how many conditions overall? Now you multiply together to get the number of groups. 2 times 3 is 6. Let's see, times 2 is 12. Times 4 is 48. We have 48 groups that we would need. So in factorial designs, the label tells all. A 2 by 3 factorial design, you have 2 independent variables because you have 2 numbers here. The first independent variable has 2 levels. The second has 3 levels. And then you multiply together 2 times 3, that's 6. We would need 6 groups or conditions. And you can have, in this case, we've got a 2 by 2 by 2. Now we have 3 independent variables or 3 factors, 1, 2, and 3. All 3 independent variables have 2 levels, and that leaves us with 8 unique conditions or 8 groups, 2 times 2 times 2. So if a study manipulated the number of hours that participants studied, 4, 6, or 8 hours, the type of study technique, shallow or deep processing, and whether participants studied individually or in groups. What are our independent variables? Well, they are number of hours studying, type of study technique, and whether they studied individually or in groups. And what's the factorial notation? Well, our first independent variable, number of hours, has 3 levels, so that's a 3 by 2 by 2. How many groups? You would multiply that together. 3 times 2 is 6, times 2 is 12. Now, how do you interpret factorial designs in SPSS and in kind of handwritten? Basically, when we look at factorial designs, we're looking for what we call main effects and interactions. The definitions are complicated. Hopefully by the time we finish this, they'll make sense to you, but a main effect, they say, is the statistical term indicating that on average an IV had an effect on a DV collapsing across the other IVs. And an interaction is a statistical term indicating that the effect of one IV on the DV is different at different levels of the other IV. Again, I know those don't make much sense, so we're going to go through what that means. So first of all, we're going to look at main effects. Did an independent variable have an effect on the dependent variable? And basically, when you're looking for main effects, you're looking at the effect of each independent variable without considering the second independent variable. So in a 2 by 2 design, there are 2 main effects. You have a main effect of the first independent variable and a main effect of the second independent variable. You'll have a main effect for each independent variable you have. So in this case, again, we're looking at the effect of age and test interval on memory performance, and each of our independent variables has 2 levels. And so our questions for our main effects, we have a main effect of age, and the question is, what effect does age have on test performance regardless of test interval? So on average, do 6 and 10-year-olds perform different in their memory scores, regardless of test interval, or we say averaging across test interval? And then we have a main effect of test interval. What effect does test interval have on performance regardless of age? So on average, do immediate and delayed recall conditions differ in their performance regardless of age, or collapsing or averaging across age? Okay, so here we have our data set up in a table like this, where we have our 2 independent variables or factors along the edges of the table. So we have age, 6 and 10-year-olds, and test recall, immediate or delayed. And these are means in here, so they're not individual scores, imagine you had 20 children who were 6-year-olds who took the immediate recall test, and their average score on the test was a 10. And then we had 26-year-olds who took the delayed recall test, and their average score was a 4, their mean. And 10-year-olds who took the immediate recall test, their average was a 14. And 20 10-year-olds who took the delayed recall test, and their average was a 12. So these are group means, not individual data points. Now, to work out the main effects, the first thing we have to do is create what we call marginal means. And marginal means are pretty simple to do. If you kind of draw your table out like this and then extend your lines, and this is what you'd want to do on a test or in your homework, and put your M here for marginal means. And then all you're doing is averaging. So you're taking 10 plus 4, which is 14, divided by 2 is 7. And then you're going to average across this row. 14 plus 12 is 26, divided by 2 is 13. And then you're going to average down the columns. 10 plus 14 is 24, divided by 2 is 12. 4 plus 12 is 16, divided by 2 is 8. So these are just the averages of the rows and the columns. Now keep in mind, if you had a homework or a test question that there were 3 age levels, like 6-year-olds, 10-year-olds, and 14-year-olds. So you had 3 numbers here, 3 rows. Then you would add the 3 numbers together and divide by 3, right, to get your average. So you're just doing an average, and these are our marginal means. And to look at the main effects, you look at the marginal means. You kind of at that point ignore your data in here, and you look at the marginal means. And if you were looking for the main effective age, so the question is there an effective age? Is there an effect of being 6-year-olds or 10-year-olds on your memory, regardless of whether you take an immediate or delayed recall test, or averaging across whether you take an immediate or delayed recall test? So what do we see here? 6-year-olds on average get 7 right on the test, and 10-year-olds on average get 13 right on the test. And so because these numbers are different, we would say we have a main effect. And what's the main effect of age? The main effect of age is that 6-year-olds tend to perform more poorly on a memory test than 13-year-olds. Okay, and we also need to then look at the main effect for test interval and compare immediate recall versus delayed recall. And again, we're going to go look down here at the marginal means to compare the marginal mean for immediate recall compared to the marginal mean for delayed recall, regardless of age. So the question for the main effective test interval is, do children tend to perform better or worse on immediate recall compared to delayed recall? And so we look here, and we've got a 12 for immediate recall, and their average score on delayed recall is 8, again, regardless or collapsing across age. And so we would say, yes, these numbers are different. We have a main effect of test interval, that children who take an immediate recall test perform better than children who take a delayed recall test. And then this is basically what I was just telling you in terms of describing the main effects, and this gives you a little summary of how to say it. The main effect of age indicates that 10-year-olds answered more questions correctly, and then you put the marginal mean in here, which was 13, than 6-year-olds, and the marginal mean of 7. And for test interval, you would do the same thing. All right. Now, we've got 2 factors, and we've looked at the effect of each factor separately, collapsing across the other. But now the question is, how do these 2 factors work together? And in fact, that's why we put them both in a study together, in that you can see the interaction or the way these 2 factors work together. And when we're looking at how the factors work together, we're going to go back and look at the cell means. So now for interactions, we're looking here in the cell means and not the marginal means. And so our question for an interaction is, does the effect of the independent variable depend on the level of the other independent variable? And when you're looking at interactions and trying to explain what's happening in your data, you can kind of tell that you're going to have an interaction if you end up using the word "it depends." So if my question is, does age have an effect on memory score? And you have to say, well, it depends on the test interval. Well, then you're probably going to have an interaction. And so let me just see here. Interactions, when you graph them, sorry, now my computer doesn't want to, there we go. Can I go backwards? Sorry, guys. When you graph interactions, your lines are not parallel. It doesn't matter if they are crossing or if they are what we call spreading interactions. You know you're going to have an interaction if the lines are not parallel. So when you graph these cell means, you'll present them in a line graph, and you're looking for non-parallel lines if you're going to have an interaction. And so this is our graph here where we have 6-year-olds and 10-year-olds. Something needs to be on the x-axis. And then I have separate lines here for immediate versus delayed recall. And so you can see we plotted the 6-year-olds at delayed recall, I think got 4 correct. And then 10-year-olds at delayed recall got, I don't know how many that is. You can look back at your chart. And then the 6-year-olds at immediate recall and 10-year-olds at immediate recall. And you can see here that we do not have parallel lines. We've got lines that are kind of coming together here at 10 years old. They're farther apart at 6 years old. So we know we're looking at an interaction. And when we describe the interaction, we're just describing the pattern of what we see here. So I might say something like, there is an interaction between age and test interval, in that at 6 years old, children perform much worse on delayed recall compared to immediate recall. But at 10 years old, there's not a very big difference in their performance between immediate and delayed recall. That's the idea of it depends. If someone was going to ask, what's the effect of immediate and delayed recall on test performance in children, I would have to say it depends. At 6-year-olds, at 6 years old, there's a big difference. Children perform much better on immediate recall compared to delay. And at 10 years old, there's not much of a difference. So we're looking for patterns. Parallel lines, we have an interaction, or no interaction, sorry. If they're non-parallel lines, you're looking at an interaction. Now, this is not statistically, I'm not looking here at statistical significance. I'll show you that on your SPSS printout. So here's our graph. And this is basically what you're saying. For 6-year-olds, performance is much higher with immediate recall testing than delayed. And for 10-year-olds, immediate testing is only slightly higher than delayed testing. And you're just coming up with your own words to describe what you see in the graph. So in other words, the difference between immediate and delayed testing is larger for the 6-year-olds than the 10-year-olds. And you can see how to describe the interaction. And it's just basically what I said. Usually point to the figure as seen in figure 1, the interaction between age and test interval. Indicate that for 6-year-olds, more questions are answered correctly on the immediate test than on the delayed test. However, for the 10-year-olds, performance is nearly identical under both conditions, with only a small decline in the number of questions answered correctly on the delayed test. So when you have a 2x2 factorial design, you've got to look for a main effect of your first variable using the marginal means, a main effect of the second variable, and then the interaction between the two. So what I want to do, instead of trying it this way, is go into SPSS. and show you, here we have a type of notes, either taking notes on a computer or handwritten notes. So that's our first variable, type of notes. We have students broken up into type of GPA, either students with a high GPA or a low GPA. And then their dependent variable is our test score. So we've got two variables with each with two levels, a 2x2 design, type of notes, GPA on test score. And here's our data. If we were to analyze this, we can go into univariate general linear model. We put our dependent variable of test score here. We have our fixed factors. Those are our two independent variables. I'm going to click on plots to get a graph. When I do this, in terms of separate lines, I usually put separate lines as something that are categories, two different categories, like type of notes. Those are separate lines. And GPA is a number. I usually put that on the axis. And then add, continue. These are the estimated marginal means. I'm just going to bring everything over so we can look at that. I don't think we need, I'll put descriptive statistics anyway. And then hit OK. So we've got our type of notes, computer versus handwritten, high, low GPA, and down here are descriptive. So people with a high GPA who took computer notes, here's their mean, 88.5 on some kind of test. Their standard deviation, we had 6 people in that group. Computer notes with a low GPA, here's their mean of 72.33, and there we had 6 people in that group. People with a high GPA who took handwritten notes, there's the mean, and again, 6 people. And people with a low GPA and handwritten notes, here's their mean. So that's the statistics. Now, in our test of between subject effects, we have type of notes. This is the main effect of type of notes, main effect, with 1, and we always do it over error, so 1 and 20 degrees of freedom. And the F ratio, does this for you, is 30. Here's our significance, 0.000. That's less than 0.05. So we have a significant effective main effective type of notes. Now GPA, this is the main effective GPA, again with 1 and 20 degrees of freedom. Here's the F ratio, and the significance is less than 0.05. So again, this is statistically significant. And then this one with the little asterisk, this is the interaction. The type of notes by GPA interaction. Here's also 1 and 20 degrees of freedom. There's your F ratio, and that is significant. If you need to go beyond that to know what things are, we've got marginal means, estimated marginal means here. So SPSS computes this for you. So for type of notes, computer, people got on average an 80, regardless of high or low GPA. Compared to handwritten notes, here's the marginal mean for handwritten notes, 87.7. So we know, we looked here, we said, oh, we do have a statistically significant main effective type of notes. Now, which type was better? You look here at your estimated marginal means, and you can see handwritten notes. People did better than using computer notes. Again, you can go back up to say, oh, we have a statistically significant main effective GPA on test score. And how, in what pattern is that? Well, people with a high, here's our estimated marginal mean, high GPA had a higher score on the test than a low GPA. Okay. And then in terms of our interaction, we said we know we have a statistically significant interaction. What's going on? Well, in that case, let's look at the graph. And what do we see here? Well, how does type of notes affect test scores? And I would say it depends. For people with a high GPA, there's almost no effect of taking computer or handwritten notes. It almost doesn't matter. But for individuals with a lower GPA, there is a big effect, and people tend to do better on tests. People with a low GPA tend to do better on tests if they take handwritten notes compared to computer notes. And that's how I would describe that interaction. All right. I hope that was helpful, everybody. Thank you. Bye.